Hi guys, welcome back to the channel. It's been a while since our last video, and today I want to take the opportunity to give you an update about the latest developments on the software for the DRDRO device. I've been working quite a bit on adding some features and fixing some bugs and making the device more flexible and easy to use. And that's what we're going to be looking at today. I was able to finish my linear scale mount here on the Cincinnati number 2. The mount I had previously was interfering, and I wanted to find a solution that would allow me to mount the scale without drilling any holes on the table or on the castings of the machine. And I think this solution is a decent one. I plan on putting a linear scale here so I can actually use the entire travel distance that I have available on this table. But this is the scale that I had on hand, so for now I'm just using this one, which will work perfectly fine to show you some of the changes and some of the features that I have available now on the DRO display. I'm going to show you some of these changes and I'll go through them so you guys can download and update the software on your devices if you're interested. And you can also understand a little bit better how they work and what is the added functionality that you have thanks to these changes. So let's go right through it and we'll see how this works. Very well. So I got you on a different angle now. Hopefully the screen is readable. There is a bit of reflection. Maybe this way it's better. So let's go and start from the changes that you will find on the main screen. We decided to use better icons for the zeroing. It's a minor thing that you will see here on the right side of the screen. This is your zero button. We had the text to zero before. Now we have an icon, and as you can see, this is doing exactly the same as before. So very minor change on that. Nothing of big relevance. The first big change comes to the origins. We did not have origins working before on the display. If you look at this second button here, we see that right now our origin is P0. That means position 0. Right now you can go ahead and change this. You can have, I think, up to 100 positions, so from 0 to 99. I'm going to just show you how this works. So if I go and choose position 1, I can set an offset on my coordinates here. For example, I can set 10 on this one, 20 on this one, 30 on this one, and 40 on this one. So this will represent our origin or our coordinates for position number 1. If I go ahead and switch back to 0, you will see that our coordinates go back to the 0 we had on the previous position. You can specify different origins representing different Z heights, for example. The most common use on a mill, in my opinion, is still to have origins that represent different coordinate systems. What that means is that if you have a mill with, for example, 2 vices mounted on it, you could have multiple origins representing coordinates specific to each one of the vices. So that would be another use case. Now, in the case of a lathe, the origins are even more useful because that's the feature that is used the most, especially if you keep your tool post in a fixed position, or if you have a multi-fix post, then you could have all of your tool carriers numbered, and then you can associate that number to an origin. And then you can have a fixed reference to that origin, which will represent the offset of the tool that you're using. So you can swap tools in and out, and you can still have a repeatable and consistent diameter and distance from your chuck. So honestly, that's the feature I use more often. That's the one that I find to be more convenient. I don't use it as much on a milling machine because it's harder to keep track of the tools, and most of us don't have, for example, a CAT 40 or a repeatable work holding solution. There are options, of course. You can use, for example, the Tormac tool system on a Bridgeport or on a small milling machine, or you might have a CAT 40 taper spindle on your machine, in which case you would have enough repeatability. But for most scenarios, if you're using R8 collets, whenever you swap a tool with the R8 collet, you're going to have a different coordinate system every time. So it's a little bit harder to use it in that case. Nonetheless, if you meet the requirements, you can have your different offsets for the tools. And for sure, you can use it for X and Y to define different origins for different vices on your table. So the only coordinate you would have to configure when you change the tool would be the Z, but everything else will stay the same. Another note is that the position number will store only the coordinates. So if you have intentions to save these ratios, for example, that is something we're not storing right now. We could add that feature if there is a need and if there is a demand, but right now I'm just storing the offsets that we have for our coordinate system. Now, the next thing I changed on the display is about our rotary axis. If you remember, we had two display values here in this first column of the rotary table row. Those two columns represented the actual and desired position for the rotary table. I thought that was redundant. It doesn't really serve any purpose for a final user. It's mostly for me, for debugging purposes. So I removed that. And I also simplified the way that you can reset your current coordinate system value. If you look at this right now, we are displaying that the motor is at 190.35 degrees. Let's say I wanted to zero this. I can just press on this button, press zeroing here, and this will reset what the current value is for our rotary table or for our dividing head. So that is an added feature. We didn't have that before. It was tricky to reset things before. You can follow an axis and do indexing at the same time, and the final position calculated by the system will be always consistent. I can show you if we now enable our y-axis and we move our axis. As you can see, this guy is working just fine. And there will be a little bit more that I want to tell you about the changes that I have made on the ratios to make it easier to use for anybody and to make sure that it's well understood how everything works. One other small minor thing, which is just cosmetic, is we had the speed bar on top, which some people find it to be confusing because of the location where it was placed. So I took that bar and I moved it under the current coordinate position number. So that bar will show you your speed when you're moving manually. If you're moving fast, for example, for a flute grinding operation, you might be moving fast back and forth. You can keep track of your speed by looking at this bar, and you just need to make sure that you don't hit the maximum. Because once you reach the maximum, the axis follower will not be able to keep up with your motion. So the motor will lag behind the real position of the axis that you are actually tracking. So you never want to go faster than what this bar is displaying you. Then we have one additional feature which I have been working on for a while, and I think it's very useful. That is the jog mode. I'm going to open this jog mode page right now so I can show you how this looks like. And we're also going to reposition the camera a little bit so you can see a little bit better on the motor itself what is going on. Okay, so we are now looking at the jog page. The jog page is pretty much a free spinning. It allows you to run the motor at a given speed, and it will run until you decide to stop it. So it will keep running without any specific destination. It just keeps running all the time. What you have to do to use this is just specify the speed at which you want to run. So I'm going to set this, for example, to 1000. Let's now go ahead and press start, and you can see that our motor is now spinning, and it's going to continue spinning at the speed you select for as long as you want, or at least until you press the stop button. You can change the speed on the fly, and it will also perform proper acceleration and deceleration ramps based on the value you set. I don't know what the maximum of speed is for the system right now, but 3000 is working just fine. Let's see if we can go a little bit higher. Okay, I guess 4000 is also doable. Maybe you can go to 5000. I have a weak power supply right now for my motor, so I cannot really push it to the limits, but this is already an excellent grinding speed, at least for my needs. So I definitely have been using it with this configuration, and it worked out very well. As you can see, the machine will perform the ramps as it is needed. It will follow and run at the speed that you want. You can do turning operations, let's say on a mill, for example, this way or in general. I think it's very useful, especially when you're doing tool cutter and grinder operations, or on some other grinding machines. That's definitely a very common application for this. So I'm going to stop here for now, Now we can exit. Now the last thing I want to show you is how the ratios work with the new math engine that is configured in the system. I have made a significant amount of changes on that to allow the software to run faster and to allow more complex mathematical operations. That was a big requirement, especially if we wanted to, for example, have a combined axis configured on the display. That is something that would have not been possible with my previous engine. With the current one, it is much easier. So that is one of the big features that I want to implement soon. It will be very handy when you use the display, for example, on a lathe, if you want to use the compound, or on a Bridgeport where you have a table and a quill, and you may want to combine those axes, and you may want to combine them at an angle. Let's say you have your quill tilted 45 degrees. You may want to keep track of your coordinates on X, Y, and Z, even when the quill is set up with an angle. And that is definitely doable. There is some setup work to do for the user. That is not straightforward. I would consider that an advanced operation. But nonetheless, I want the device to be able to do it. If the user wants to do it, I want to be able to do it with the display. So we will be working on that for sure in the next months, especially during the winter time when there is not much going on outdoors. I think I will find more time to actually implement these features on the display. So what are these changes? Let's go through some of them. The original version had no real good concept of numerator and denominator. They were absolute numbers. That's how we implemented it originally, which was not convenient, especially for us Americans working with the imperial system. You would have to do calculations. You would have to figure out values with your calculator. It was just not user-friendly at all. If you were working in millimeters, yes, you could make it work 100%, and it was somewhat easier to configure. But if you wanted to work with the imperial system, it was a big pain to set it up. So what I changed in the system now is that these numbers will always refer to the units that you are displaying. What this means is that, for example, here we have the y-axis, which is configured to track the motion of my table. And it should be called X, by the way, but disregard that. So the y-axis right now is displayed in inches, right? So we have 1.176 inches. And then we have an output axis, which is working right now in degrees. So what we're saying with these two numbers here is that for every 1 inch of travel distance of my y-axis, which is our denominator, we will travel 90 units of the output axis. In this case, we're working in degrees. So what this means is that 1 inch of travel on the y corresponds to 90 degrees on the output axis, which is our dividing head here. So let me see if I can demonstrate it to you. I'm going to set up a dial test indicator, and we will demo this so you guys can get a feeling about how this works. All right, guys, this is a tricky setup. Hopefully you can see well enough. I am trying my best. I know light is not perfect, and yeah, it's definitely hard to read. What I'm trying to do here is I have a dial test indicator, a digital one. Hopefully it's more readable than the analog ones. And then I got the display with the coordinates for the y-axis. This is just to verify that whatever number we see on the display is correct and matches the value that the dial test indicator is giving us. I'm in inches, which is one of the things that I wanted to showcase here for the ratios configuration. So let's see if we go now to, let's try to go to close to 100 thou. So we are at 100 there. This is 100, so that's great. We can go in more and go to, let's go to half inch, 5056, 5053. So we are very close. So that confirms to us that the scale is configured correctly. The ratio for the scale is configured correctly. And it confirms to us that the scale is also accurate and it's fairly linear, at least in this half-inch travel distance. It's telling us that the machine is pretty much set up to do whatever we want it to do. So what I'm going to do next is I'm going to take a marker and we'll try to put a mark on the dividing head so that the ratio configuration will be testable, and then you guys can see how it works. Okay, guys, I repositioned the things a little bit here so they make a little more sense. And hopefully you can get a better view of what's going on. What you can see here is that the display is working with what we call the y-axis here. We got our input working in there, and in your frame you also see our motorized workhead. I want to show you how the normalized ratio now allows us to configure a distance in inches to be translated into a rotation of the head in degrees. I'm going to make a small mark here now so we can identify the 0 and the 90 degrees rotation. So visually we can have a confirmation. And once that is marked, we will use the synchronized motion to actually make sure that 1 inch of travel for the y-axis translates into 90 degrees of rotation for our tool. Okay, here we go. So this is going to be our first mark here. This is the 0. I'm going to now set this to 90 degrees, which goes right there. I'm going to make our second mark right here. Okay. Hopefully the alignment is not horrible. Let's see how bad it is. Go back to 0. Okay, I think that's good enough. It should be good enough to at least prove what we're trying to demonstrate here. So as you can see now, the display is showing current position is 0, offset is 0. We got our y-axis, which is at 0.2. So I'm going to reset this. I'm going to put it to 0 so it's easier for us to read. I'm going to now enable the synchro mode. And now, let me see if I can use the slow feed. Now we're going to move 1 inch. We're going to go 1 inch. And what we expect to see is that at 1 inch, we're going to be exactly at 90 degrees. And as you can see, this works exactly as we expected. So let's go back and reposition our table so that it is at 0. Now, what I want to show you is what changes when you actually switch mode to millimeters, okay? So let me disable this. I'm going to reset all the axes so we're back to 0, 0 everywhere. With the current configuration, we're telling the system to turn 90 degrees for 1 millimeter of travel distance, which is very aggressive. That would definitely be a problem if we try to do that because the motor has to step very quickly to keep up, especially with the resolution of my scale, which is 5 micron. So before even trying that, I can show that to you in a second. But first, I want to show you the real working case. Let's say we want to do 90 degrees of rotation with, let's say, 50 millimeters of travel distance, which is a more understandable and reasonable ratio to apply, especially with this configuration. So let's get this one set to 0 again, because I moved the table inadvertently, and let's turn this on. So what we expect now to see is that the current position and our marker go to 90 degrees when the travel distance is 50 millimeters. So let's go ahead and try that and see if the machine does what it's supposed to do. And sure enough, as you can see here, the ratio has been calculated perfectly and we are tracking our axis exactly as we want it to. So let's give you this silly demonstration as well, since we were talking about it. What happens if the ratio is terribly wrong? I'll show you. Let's set this one to 1 as it was before. So 1 millimeter of travel distance will be reflected into 90 degrees of rotation. This is a very aggressive ramp, and I would not recommend anybody to even think about doing something like this. But if you have a mistake, that's what you're going to see happening. So as you can see how fast the motor is stepping through? So what is happening is that anytime we have a change in the reading in our scale, the required travel distance for the motor is bigger than 1 step. So the motor steps multiple times for each individual change, each unit change on the linear scale. It's kind of a stepped rotation on the motor, because the motor needs to travel significantly more compared to the steps that we're reading from the linear scale. Sure, you could have a high resolution scale and that would allow you to have a steeper ratio, okay? That's always possible, but is it recommended? I still think it's not a very good solution, especially because what happens is that when you do, let's say, 4 or 5 steps of rotation with your workhead, your speed is the maximum speed that the motor can run at. There are ways to do those operations without facing or incurring into this limitation. But that's, the system will do it, right? It will calculate it for you. We could even be more aggressive. We could say do 180 degrees instead of 90 for us, and it will do it. See how fast it's moving now? Now, is this reliable? Definitely not. I don't think it's something you should do at all. But the system will do it for you. And it will do it. It will follow the position that you want. It's just every step that you rotate, every time you request a rotation, you see, that's how much the head has to travel to keep up with the ramp you requested. Let's put it back to something more normal. Let's say 90 degrees on a distance of, let's say, 50. And then you will see how smooth the motion is. See how smooth the motion is now? That is because the motor does not have to run so much for every increment that he reads from the linear scale. And the result is that your machining is smooth, or at least is the smoothest that your motor and your ratio on the workhead allows you to achieve. So yeah, that's pretty much it. So as you can see, we have normalized ratios, very useful also, for example, when you're doing threads in ELS mode, something that, again, I want to cover more in detail. Jeremy makes things. He has made a very nice video with his lathe covering use cases for this. And I encourage you to look at his video if you want to get an idea. He was doing it with the first version of the display, and we had to calculate things with our calculator and set parameters manually to achieve the ratios he needed. So, that was a lesson learned. I understood a little bit better what could be an ideal use case for the DRO in ELS mode. And this is the resulting version of the engine, at least. The UI still needs work, and I have some other contributors and fans of the project who suggested great ideas, and sure enough, I'll be working on those as soon as time allows. It's always just a matter of time. So we will get there. We will have all the features. We'll make them user-friendly for tapers, for thread cutting, for dividing, for cutting gears, for helical gears. You name it. We will make it all much more useful than it is right now. At the current stage, you can see this as more like an engineering tool, which is very general purpose, but it requires you to know how to set up those parameters, and it requires you to know a little bit of math or at least geometry so that you can configure these parameters to suit your needs. It's definitely, everything is doable. It's just not as user-friendly. So we're going to change that. We're going to make nice tables for the ELS mode where you can pick your feed rates and your threads. We can have a set of predefined values for metric and imperial, and have all the TPIs and all the modulos configured in nice tables. So for the user, it's very easy to set it up. So that's all planned in the future. The system already is capable of doing it. It's just, yes, user friendliness is not there yet. Well, guys, I hope you enjoyed this quick review of the changes that we have on the DRO. All the software, as always, is available on GitHub. So please go ahead, take a look. If you're a software developer, please review and comment and provide any kinds of suggestions that comes to your mind. A few guys have done it already. I really appreciate the feedback. Sometimes it's hard to know if what you're doing is right or not, especially because you're using it every day. You're writing the code. So you might be doing something silly or something too complex to understand, and you don't realize it until you have somebody else who actually plays with the device and tells you, hey, this thing doesn't work well. This is complicated. This is silly. And, the feedback is great. And ideas and suggestions are absolutely what drives the project. And, it's great to see that many people are interested into the project and that you guys are using it. So I'm really happy about it. So please don't stop doing that. And I'll continue making improvements and adding features to the display. And hopefully you guys like it. So until the next time, reach back if you have any questions or comments. All right. Thank you very much.